In this video, we solve problem 8.5.017 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to use partial fractions to evaluate the indefinite integral, and this is it. So the first thing that we do whenever we are faced with an integral is we ask ourselves if basic rules apply, and we don't have basic rules for this. We've got a polynomial over a polynomial. The next thing we would say is, okay, if that doesn't work, what about u substitution? Now, whenever I'm using u substitution, I'm looking for a function inside of another function. So I'm looking for a function under a radical, in an exponent, in parentheses somewhere, inside a trig function, inside a logarithm, something like that. And we don't have any of that. So what I tell my students in Calculus 1 is if there are no parentheses and there don't seem to be any grouping symbols, often if you have a fraction, u would be the denominator. If a u substitution is going to work, we might let u be this whole denominator. Well, the u substitution will only work if the derivative of this, or some multiple of the derivative of this, is up here somewhere as a factor. The derivative of x to the fourth minus 20x squared minus 125 is 4x cubed minus 40x plus 0. And there's no 4x cubed minus 40x up here. And there's no 4x cubed minus 40x times a constant up here. So that's not going to work. Also, we're in this section on partial fraction decomposition, and we're told to use partial fraction decomposition to evaluate this. So we know that that's where we start. Okay, so now I'm looking at this integral and I'm asking myself, what is the appropriate partial fraction decomposition for something like this? Well, and actually, before we do that, we have to say, look at the degree of the numerator and degree of the denominator. Since the degree of the numerator is less than the degree of the denominator, I know that partial fractions are going to work. So I guess I should write that down. We want to start by doing that. So I'm saying the degree of the numerator is less than the degree of the denominator. Since that's true, we know we're ready to use partial fractions. And I'll use the abbreviation PFD for partial fraction decomposition. And after you've done that, after you've realized that you're ready to use PFD, you want to state the appropriate partial fraction decomposition for that expression, for that rational function. And the way we do that first is to factor the denominator as much as possible. So I've got x to the fourth minus 20x squared minus 125, and I want to factor that. Now, since there's an x to the fourth here and an x squared here, this is an expression that's quadratic in form. So while it's not a quadratic equation, it has the form of a quadratic equation because x squared squared is x to the fourth. So rather than factoring this with an x here and an x here and a constant here and a constant here, if I use x squared here and x squared here, this can otherwise be factored in almost exactly the same way that I would factor a trinomial where that was an x squared and that was an x. We're just having x squared playing the role of the x here, if that makes sense. So now I need two numbers that multiply to give me 125 that add to negative 20. So I need a product of negative 125 and a sum of negative 20. Now, if the product is negative, that means one of the numbers has to be negative and the other one has to be positive. And then we want the numbers to actually have a difference of 20 because they're going to have opposite signs. So I think 25 and 5 will work because 5 times 25 is 125. And those have a difference of 20. Now I need to make one of these negative and the other one positive so that when I add them together, I get negative 20. So it must be a negative 25. Negative 25 times 5 is negative 125, and negative 25 plus 5 is negative 20. So that's going to work. So we'll put that here, negative 25 here, and the plus 5 over here. Now at this point, I look at this again and I think about this as if I'm starting from scratch and I ask myself, does it factor any further? Well, that's x squared plus a constant. That doesn't factor, not in the real number system. So that's an irreducible quadratic. But this is something of the form a squared minus b squared. And you want to recall from algebra class, probably in high school, that that difference of squares factors that way. It's a plus b times a minus b. So my a here is x, and I'm subtracting 5 squared. So I want to add 5 and subtract 5. So that is my denominator. It's factored as much as possible. And now I want to state the appropriate partial fraction decomposition, given that this is my denominator. The form of the partial fraction decomposition depends on these factors down here. Since this is a linear factor and it's not repeated, we just get a constant over that factor as a term in our partial fraction decomposition. And then we've got another linear factor, not repeated. So we're going to have a constant over that factor in the decomposition. Now this is an irreducible quadratic. Whenever you have an irreducible quadratic, it appears in the partial fraction decomposition this way. Instead of having a constant in the numerator, you get a constant times x plus a constant up here. Since this is degree 1, this term in the numerator has to be degree 0. So the degree is always 1 less. So we just get constants here. This is degree 2. The degree in the numerator has to be 1 less than that. 1 less than 2 is 1, so we have a degree 1 polynomial in the numerator. So that's the partial fraction decomposition, and we want to find the values of a, b, c, and d such that this expression equals this expression. In order to find a, b, c, and d, we'll take this equation and we'll multiply by the LCD. And the LCD is always the original denominator. So I'm multiplying everything by x plus 5 times x minus 5 times x squared plus 5 all the way across. And there's not quite enough room over here. That's okay. We'll do x squared plus 5 times x plus 5 times x minus 5. And then because we've multiplied by the LCD, all of those denominators should reduce. So the x plus 5s reduce, the x minus 5s reduce, and the x squared minus, or x squared plus 5 reduces. The x squared plus, or the x plus 5 reduces there, the x minus 5 reduces there, the x squared plus 5 reduces there. And now all the denominators have canceled or reduced, they're gone. And we're left with this equation. We've got x squared over here equals a times x minus 5 times x squared plus 5. And then we've got b times x plus 5 times x squared plus 5. And then we'll have cx plus d times x plus 5 times x minus 5. To save myself a little bit of work, I'm going to distribute that right now. X plus 5 times x minus 5 simplifies to x squared minus 25. And if you don't believe me, FOIL, first times first is x squared, outer times outer is negative 5x, inner times inner is positive 5x, negative 5x plus positive 5x is 0x, the x's are gone. And then we've got that negative 25 on the end. So we're here now. Now our goal is to solve for a, b, c, and d. One way that we can solve for some of these constants is to choose a value of x that would make some of these factors equal to 0. Now we can't choose a real number to make the x squared plus 5 equal 0, so that's not going to work for the entire problem to find all of the coefficients or all of those constants a, b, c, and d. But by letting x equal 5, I can make that factor a 0, and by letting x equal negative 5, I can make that factor a 0. And that's going to help us to find at least some of the constants. So we'll choose, or we'll say, let's let x equal values that cause the factors of our original denominator to be 0. And it's a very wordy way of saying it. I can't think of a better way myself, I'm sorry. But the reason we're doing that is because when x equals 5, let's say, if that factor is 0, that means that entire factor is gone. The entire term is gone in this equation. And that's what we want. We want to simplify this as much as possible. So when x equals 5, the left-hand side is 5 squared, or 25. And we have a times 0 times 25 plus 5 is 30. And then we're going to have b times 10 times 30. And then we'll have cx plus d. And, oops, it's going to be c times 5 plus d because x equals 5. And then we've got a 5 squared minus 25, which is 25 minus 25, or 0. So because x was equal to 5, this term is gone. And this term is gone because anything times 0 is 0. And we end up with this, 25 equals 300b. And that means that b equals 25 divided by 300. You'd say, well, how many times does 25 go into 300? I think it goes in 12 times. So we've got that right there. And if you're wondering like, how you might do that quickly, I think $3 is 4 quarters times 3, so we'd have 12 quarters left. So that gives us our b, and similarly, we'd like to, instead of setting x minus 5 equal to 0 this time, we'd like to set x plus 5 equal to 0. So x plus 5 is 0 when x equals negative 5. So we substitute that in. We'll have negative 5 squared. Negative 5 times negative 5 is positive 25. And then we have a. Negative 5 minus 5 is negative 10. Then we've got 25 plus 5, which is 30. If x equals negative 5, we have a 0 right here. b times 0 is 0. And if x equals negative 5 times negative 5 is positive 25, because negative times negative is a positive, so we'll have 25 minus 25. So 0 times something is going to be 0. So this term is gone, and all we're left with is this, and that's enough to get us a. So that simplifies to 25 equals negative 300 times a. So a must be 25 divided by negative 300, or negative 112. Now the last thing that we could do is set x squared plus 5 equal to 0, but that would mean x equals plus or minus the square root of 5 times I, and we don't want to plug in complex numbers here. Okay, so we found the values of a and b, but the question is, how do we find the values of c and d? One way that we can find the values of c and d is distribute and then collect like terms in x, and I'll show you what I mean. So first we let x equal values that cause the factors to be 0, and we solved for a and b. And now we have to use some other method to find c and d. So we're going to go back up to this equation and distribute. So we've got x squared on the left-hand side equals a times, and if you FOIL, first times first is x cubed. Outer times outer is 5x. Inner times inner is negative 5x squared. And then last times last is negative 25. We'll do something similar over here with the b. First times first is x cubed. Outer times outer is 5x. Inner times inner is plus 5x squared. And last times last is 25. And then when we multiply cx plus d times x squared minus 25, first times first is going to give me cx cubed. Outer times outer is negative 25 as cx. Inner times inner is dx squared. And then last times last is negative 25d. And we keep distributing, so distribute that a through everything. distribute that A to all 4 of those terms there. We're going to do the same thing with B. Okay, now this next step, we're doing this next step for a reason. I just want you to know why we're doing what we're doing. Here's the idea. 2 polynomials are equal if and only if their coefficients are equal. So if I had something like this, x squared minus 2x plus 1 equals ax squared plus bx plus c. The only way that could happen is if the number multiplying x squared on this side was equal to the number multiplying x squared on this side. So the implied 1 over here would have to be a. And the number multiplying x on this side has to equal the number multiplying x on that side. So that number multiplying x, the b over here, would have to be -2. And the constant term would have to be c, so c would have to equal 1. That's just because these functions, x squared, x, and 1 actually, are linearly independent. And we'll talk more about that in differential equations. So with that in mind, I've got a polynomial on this side. It's just x squared. On this side, I have a cubic polynomial. The highest degree terms are all a constant times x cubed. So they're degree 3 terms. So I want to write this as a cubic polynomial on this side by grouping all of the x cubed terms. So I've got an ax cubed here, bx cubed here, and a cx cubed there. So that's a plus b plus c times x cubed. And then we want to group the x squared terms. So we're just grouping like terms in x. We've got -5a times x squared plus 5b times x squared and a d times x squared. I guess I didn't leave myself enough space, so we'll say plus d times x squared. That's there. And then we want to group the x terms together. So you've got a 5ax and a 5bx and a -25cx. And I think that's all of our x terms. And then finally, the constant term is this plus this plus this. And I've run out of space, so I'm just going to write it up here. So plus -25a plus 25b minus 25d. So it's this plus this plus this plus this. Has to equal this quadratic over here. Now, I don't have a cubic term on this side. I don't have an x term or a constant term on this side. So I'm just going to add some placeholders. X squared is the same as 0x cubed plus x squared plus 0x plus 0. So I'm just adding these placeholders, multiplying x cubed by 0, x by 0, and making my constant term 0. So now the terms on this side and the terms on this side are basically the same. Now, we're going to use this fact, the same fact that we talked about on this sticky note. The only way 2 polynomials are equal is if their coefficients are equal. So the coefficient of x cubed on this side has to equal the coefficient of x cubed on this side. Get another piece of paper so I can keep doing the problem. So the coefficient of x cubed on this side is a plus b plus c. So a plus b plus c must be 0. And the coefficient of x squared on this side has to equal the coefficient of x squared on that side. Well, there's an implied 1 right there. It's a little bit hard to see. So we've got -5a plus 5b plus d equals 1. So that has to be equal to that. And the coefficient of the x term on this side has to equal the coefficient of the x term on that side. So 5a plus 5b minus 25c must be 0. And then lastly, our constant term on this side has to equal the constant term on this side. And the constant was negative 25a plus 25b minus 25d equals 0. Okay. Now, this is a system of 4 equations and 4 unknowns, which would be tough to solve, but we could do it. We can systematically eliminate variables until we got our 4 equations and 4 unknowns down to 3 equations and 3 unknowns, then 2 equations and 2 unknowns, and then 1 equation with 1 unknown, then we could solve it, and then back substitute and solve that, and back substitute and solve that, and back substitute. But fortunately, we were able to do this earlier. When we let x equal 5, we found out that b had to be 1/12. And when we let x equal -5, we found out that a had to be -1/12. So we already know a and b. We can substitute those in over here and take our 4 equations and 4 unknowns and make that 2 equations with 2 unknowns. So a is -1/12 and b is +1/12. So we have -1/12 plus +1/12 plus c equals 0. Okay, well, those cancel and it looks like c must be 0. Well, that's easy enough. And then if a is -1/12, -1/12 times -5 is going to be +5/12. And then we'll have 1/12 times 5 is +5/12. And then we've got d here, and that equals 1. Well, that's going to be 10/12, right? So we've got 10/12 plus d equals 1, or d equals 1 minus 10/12, which reduces to 5/6. And that's 6/6 minus 5/6 is 1/6. So d is 1/6. Now that's just from the 2 equations up here. Now in order for this to be consistent, in order for this to be a consistent system, c equals 0 better work in this equation, and d equals 1/6 better work in this equation. Otherwise, we're in trouble. So let's make sure it actually works for this guy. If a is -1/12, this third equation becomes -5/12. If b is 1/12, that second term in the third equation becomes 5/12. And then we've got minus 25 times c, which is 0. And we put that in the equation, and the question is that true? Well, that cancels with that, and we have 0 equals 0. So yes, that's true. So that means at least our c value is consistent. So we're good there. And then let's check for this last one. I've got -25 times -1/12. It's going to be +25/12 plus 25 times +1/12. So it's going to be 25/12 again. Minus 25 times d, which is 1/6. Question is that equal to 0? Well, let's check it out. We can add these 2 guys together, and we get 50/12 minus 25/6 multiplied by 2/2 to get a common denominator. We have 50 minus 50/12 is 0. So it checks out. So good. We found out that c was 0, d was 1/6, a was -1/12, and b was +1/12. And we can go back to this original partial fraction decomposition and substitute all of those guys in here. And then once we do that, we're saying this is equal to this. And this expression is something that I can anti-differentiate using basic rules. So then we can go back and solve the original integral. All right, so we've got this. The integral of x squared over x to the 4th minus 20x squared minus 125 all times dx. That's equal to this. It's a over x plus 5, and a is -1/12. Plus b over x minus 5. b is +1/12. Plus cx plus d. Well, c was 0. So we have 0 times x plus d, where d is +1/6, over x squared plus 25. And we can evaluate this with a u substitution. We can evaluate this with a different u substitution. And that is a constant over a squared plus x squared, so that's going to be an inverse tangent function. So let's do all three of these. Since they have different values for u, I'm going to do these separately. But I think you can probably see how this is going to work. And I factored out that 1/6 for that last one. On this guy, we've got a constant over x plus 5. If u is equal to the denominator, du is equal to the derivative of that, which is 1 times dx. So this is actually negative 1/12 over u times du. Or if you prefer, you can factor out that negative 1/12. And the antiderivative of 1 over u is natural log of the absolute value of u plus c. We'll save the plus c for later. And then don't forget to back substitute. U is x plus 5. We're going to do something similar here. Except on this one, u is x minus 5. Du is still 1 times dx. So that's a u, and that's a du. So this is a different u than this u over here, so I'm just sort of keeping those separate. Then this integral becomes a positive 1/12 times the integral of 1 over u du. And that's going to give us a positive 1/12 times natural log of the absolute value of u. And u is x minus 5. So we substitute that in. And then on this last one, that's an inverse tangent function. Since a squared is 25, a is the square root of that, positive square root of 25 is 5. So we're going to have 1/6 times 1 over a times the arctangent of x over a plus c. Oh, I wrote 25. I don't know why I wrote 25. That should be a 5. Sorry. That makes it very different. A is actually just the square root of 5, not 5 itself. So we're going to have a square root of 5 here and a square root of 5 here. Now you could rationalize the denominator if you wanted to. It's not necessary. Normally I would leave this one alone, and I tend to rationalize the coefficient. I think it's just a habit from grade school when I learned how to rationalize expressions. So I'll multiply this one by root 5 over root 5. I get root 5 in the numerator, and square root of 5 times square root of 5 is the square root of 25, or 5. And we have 5 times 6, which is 30. We've got all of that plus c. So that's our answer. Now, WebAssign may or may not like this answer. I think it's probably fine with the equivalent 1 over 6 times root 5 out front. I don't think it would rationalize that expression inside, but I could be wrong about that. But I think often this difference of logarithms is condensed in textbooks. Now, in order to condense something that looks like this, we have to remember a couple of properties. If you have natural log of a minus natural log of b, you can write that as the natural log of the quotient, a over b. And if you have a constant out front, you can't use that rule. So each of those constants should be brought up inside as a factor. Or maybe we just factor the 1/12 out from everything. So let's do that. Let's factor out 1/12. And I'll put the positive one first. So this is natural log of the absolute value of x minus 5 minus natural log of the absolute value of x plus 5 plus root 5 over 30 times arctan of x over 5, or x over square root of 5. And then this has this form. So I can rewrite this as a log of this divided by this. So I've got 1/12 times the log of the absolute value of x minus 5 over x plus 5. got that right there. So that might be a form that WebAssign likes. Now we could even go further by bringing that constant inside as an exponent. There's this rule from pre-calculus or college algebra. If you have a number out front or a coefficient in front of a logarithm, that's the same as that logarithm of a to the n. So that could be brought up as an exponent. So we could bring this 1/12 inside if we wanted to. And 1/12 power is the same as the 12th root. So you might even have it like this, the 12th root of x minus 5 over x plus 5. I have to take the absolute value of that still, plus square root of 5 over 30 times arctangent of x over square root of 5. I'm not 100% sure which one WebAssign wants, but all of these are equivalent. Maybe they would have all of this to the 1/12 power, which is the same thing, and that would be fine. For a test or a quiz, I would just stop right here. This is great. And even if you didn't rationalize this, if you just wrote that as 1/6 times the square root of 5, that would be fine with me. But if we're trying to match our answers to answers in the back of the book, or trying to get the answer into a form that WebAssign will like, and we have 100 chances, or I give you 100 chances on your homework in my class, it's possible that WebAssign would want this, or WebAssign would want this. And if WebAssign doesn't accept any of these, then there might be a wrong answer coded in, and we'll just have to contact them and ask them to fix it.